Hey everyone! Ever wonder how your phone magically knows exactly where you are, whether you're navigating a busy city or hiking a remote trail? That's the Global Positioning System, or GPS, at work. It's one of those incredible technologies we use every single day without really thinking about the sheer genius behind it. Today, we're going to pull back the curtain and explore how this global marvel actually pinpoints your location, from satellites zipping around Earth to the tiny chip in your device. It's way cooler and more complex than you might think, but we'll break it down super simply. Let's dive in. And when I say every day, I really mean it. GPS isn't just about getting directions to the nearest coffee shop. It's literally woven into the fabric of modern life. Think about delivery trucks getting their packages to you on time, or airplanes staying on their precise flight paths. Farmers use it for precision planting, firefighters use it to find emergencies, and even scientists use its incredibly accurate timing for studying earthquakes. It's a silent, invisible helper making countless operations run smoothly, which is wild, by the way, how something so essential can be so hidden. At its heart, GPS is all about satellites and signals. Imagine our planet surrounded by a fleet of high-tech broadcasters in space. These aren't just any satellites, they're specifically designed to beam down a continuous stream of radio signals. Your phone, or any GPS receiver for that matter, is constantly listening for these signals. It's like a quiet, one-way conversation happening thousands of miles above us, all the time. The satellites are doing all the talking, and your device is doing all the hard work of listening and figuring things out. So, how many of these broadcasters are up there? The GPS system, which is owned and operated by the US government, actually has a constellation of over 30 satellites currently orbiting Earth. While 24 active satellites are generally considered the minimum for global coverage, there are often more, providing redundancy and improving accuracy. They're whizzing around our planet twice a day, on very specific paths, making sure that at any given moment, you can see at least 4 to 5 of them from almost anywhere on Earth, which is pretty clever engineering. Now, what exactly are these satellites saying in their radio signals? Well, two crucial pieces of information. First, they transmit their exact position in space at the precise moment the signal is sent. Think of it like a cosmic mailing address. Second, and this is super important, they include a timestamp, the exact time, down to an incredibly tiny fraction of a second, that the signal left the satellite. These two pieces of data are the fundamental building blocks your receiver uses to calculate its position. No guessing games here, just precise timing. Okay, so your phone, or your car's navigation system, is acting as a passive listener. It picks up these signals from multiple satellites. As soon as it receives a signal, it notes the exact time of arrival. Then, it compares that arrival time with the time the satellite said the signal was sent. The difference between those two times tells your receiver how long the signal took to travel from the satellite to your device. And guess what? Knowing that time difference is the key to calculating distance. Let's break down how that distance calculation helps us find our spot. Imagine you only hear from one satellite. You know how far away you are from it, right? If you know you're, say, 20,000 kilometers from that satellite, you could be anywhere on a giant imaginary sphere with a radius of 20,000 kilometers centered on that satellite. That's a lot of places. So, one satellite, while helpful for distance, doesn't tell you much about your specific location. It's like knowing you're somewhere in this giant bubble. What if you hear from a second satellite? Now things get more interesting. You'll have another imaginary sphere, centered on the second satellite, with its own radius based on the distance. Where do these two spheres intersect? They don't just touch at a point, they intersect to form a perfect circle in space. So, with two satellites, we've narrowed your possible location down from a huge sphere to a specific circle. Still not precise enough for your morning commute, but we're getting closer, which is pretty neat. And here's where the magic really starts to happen: add a third satellite. Now you have 3 intersecting spheres. If you think about it in 2D, like drawing circles on a map, three circles will typically intersect at only 2 points. In 3D space, it's similar, three spheres usually intersect at just 2 specific points. One of those points is almost always ridiculously far out in space or something impossible, so your receiver can discard it, leaving just one potential location. Bingo! That's your position, right there. This process is called trilateration. You might be thinking, hold on, if 3 satellites give me my location, why do we always hear about needing 4? That's an excellent question, and it comes down to timing. Those time differences we talked about? They need to be incredibly precise. Satellites have super-accurate atomic clocks, but your phone's clock isn't quite as fancy. Even a tiny error in your phone's internal clock can throw off the distance calculations by hundreds of meters. So, the 4th satellite is used to solve for that unknown variable, your receiver's clock error. It essentially synchronizes your phone to the super-precise satellite time. Let's quickly revisit that distance equals speed times time thing. The speed here is the speed of light, which is an astonishing 299,792,458 meters per second. It's the fastest thing we know. So, even a millisecond, a thousandth of a second, of error in measuring the signal's travel time can translate into a distance error of almost 300 kilometers. That's why the precision of those atomic clocks and the correction from the 4th satellite are absolutely non-negotiable for accurate positioning. Every tiny fraction of a second counts massively. Speaking of precision, those atomic clocks on board each GPS satellite are simply mind-blowing. They're so accurate that they would only lose about 1 second over millions of years. This level of accuracy is completely vital for the entire system to work. If satellite clocks drifted even a tiny bit, their timestamps would be off, and our distance calculations would be totally skewed, making GPS unusable. They are, without a doubt, the unsung heroes of accurate global positioning, keeping everything perfectly synchronized across the entire constellation. It's not just satellites floating around by themselves, though. The whole GPS system relies on a crucial control segment right here on Earth. This network of ground stations, scattered around the globe, constantly monitors the satellites. They track their orbits, ensure they're sending correct signals, and upload any necessary adjustments or new navigation messages. Think of them as the mission control for the entire GPS operation, making sure every satellite is exactly where it needs to be and performing flawlessly. They're the silent guardians of your navigation. While GPS is incredibly clever, it's not always perfectly precise. Several factors can mess with its accuracy. One big one is the Earth's atmosphere. Signals can slow down or bend as they pass through the ionosphere and troposphere, which subtly affects their travel time. Then there's multipath interference, where signals bounce off buildings or mountains before reaching your receiver, making them seem like they've traveled further. And, of course, simply being indoors or under dense tree cover can block signals entirely. That's why your phone sometimes struggles to get a lock. But engineers are always working to improve things. 2 key techniques help overcome some of these challenges. First, differential GPS or DGPS uses fixed ground reference stations at known locations to calculate local signal errors and then broadcast corrections to nearby GPS receivers. Second, assisted GPS or AGPS, especially common in smartphones, uses cell tower data to get an approximate position and a faster initial satellite lock, especially useful in urban areas or indoors where satellite signals might be weak. These helpers make your everyday GPS experience much smoother. It's important to remember that GPS is just one of several global navigation satellite systems, or GNSS, out there. While GPS is American, Russia has GLONASS, the European Union has Galileo, and China operates Beidou. Many modern receivers, including your smartphone, can actually tap into signals from multiple GNSS constellations simultaneously. This multi-system approach dramatically improves accuracy, reliability, and coverage, especially in challenging environments like deep urban canyons or mountainous regions. It means more satellites, more signals, and a better lock for you. Beyond just guiding your car, GPS timing signals are incredibly precise and are used for critical infrastructure around the world. Power grids use it to synchronize operations, financial networks use it to timestamp transactions, and cellular networks rely on it to hand off calls seamlessly. It's also vital for disaster response, wildlife tracking, and even weather forecasting. It truly underpins so many aspects of our connected world that we often take for granted, quietly working in the background to keep everything running on time and in place. And the future of GPS and GNSS is only getting more exciting. Newer satellites are transmitting additional, more robust signals, like the L5 signal, which offers even greater accuracy and resilience. We're talking about achieving centimeter-level precision in the not-so-distant future, opening up possibilities for widespread autonomous vehicles, hyper-accurate drone deliveries, and smart city infrastructure that can truly optimize itself. The evolution continues, promising an even more integrated and precise global positioning experience for all of us, which is pretty mind-blowing. So, the next time you use your phone to navigate somewhere new, take a moment to appreciate the invisible dance happening above you. A constellation of satellites, each with an atomic clock, beaming signals across thousands of miles, processed by ground stations, and finally interpreted by the tiny chip in your hand. It's a testament to human ingenuity and global cooperation, making our world a little bit smaller and a whole lot easier to explore. From basic directions to vital infrastructure, GPS truly is a modern marvel. Thanks for joining me on this cosmic journey.